我们说要分别叔叔请假在寝室，就是
有收到，
哦，
收到，没事。 Yeah, morning everyone. Any questions or lesson? Strictly. Yeah. Really? I mean, this one. Strictly. This one. This one. So, strictly. With this one. Okay. Oh yeah. Okay. So strictly increasing is so this one. So what's strictly increasing? So strictly increasing means g y gx less than gy for x less than y. Okay. So you want to check given x less than y, s cubed less than y cubed. Okay. So we got this y cubed. Yeah. So you found this first, and then you found this, and then you found this. Because, for example, the first one, right? So first one, because you know that x less than y, okay? Then since less than y, we can multiply by s squared. Okay. Okay. And then similarly for this, also use the same method. So this one x, y, so you can multiply x, y on the side. Yeah. And then this time multiply y squared on both sides. Yeah. Yeah. Okay. There's one rule in the book, there's no name for it. So maybe we just create a name for it and then use it for exam. So for this implication rule, which is logically equivalent to not P or Q, okay? I think I decide to call it implication extension law. Okay. So in the exam you can use it if like okay. Okay. So if you want to say something about this law, you just mention this word here. Okay. I think textbook don't have the name for this logical equivalence. Implication distinction. Okay. Yeah. Any other question before we proceed? I want to do one survey before we start. So, how many of you do you find it's difficult, like to read definition first and then see examples? Huh? Okay, you guys fine with it? Huh? Fine. Okay, you guys fine with it? Okay, good. Okay. Okay, today we will talk about number theory. I mean, just 2 weeks we will talk about number theories and cryptography. New chapter. This one is chapter 3. Yeah, but in the book it's chapter 4. So yeah, just right. In the book it's chapter 4. So this week we focus on number theory, and then next week will be on cryptography. Okay. So 4.1. So first part, we will learn modular arithmetic. So one motivation for this modular arithmetic will be the clock. So every time you will see the clock, for example, what is 12 hours after 1 p.m. So maybe you would think like it's like 13 p.m. So what's 13 p.m.? It's 1 a.m. Okay. So in real life, we already start using these mod 12 calculation. Okay. So when we talk about this modular arithmetic, we will now first define what is division. Okay. So let's take uh, A, B, okay, which are the integers, and one of them is non-zero. Okay, one of them is non-zero. So we say A divides B. Okay, I use wood first. A divides B. Okay, there's this and C such that B equals to AC. Okay. Or if you do the division, B over A is an integer. Okay. And this is denoted by B, sorry, A divided B, and straight line B, A divides B. So if A divides B, okay, then A is a factor of divisor of B, okay, and B is a multiple of A. Okay. So we write A doesn't divide B if A does not divide B. Okay. So if you are lost in the definition, let's look at this example here. Okay. Let's look at the example here. So for example, we will say that 2 divides 6. Okay. Why? Because you can write 6 equal to 2 times 3. Okay. So this 2 we will call it a factor. Right. And then 6 is a multiple of 2. But for example, 2 doesn't divide 7. Okay. Why? Because 7 is not a multiple of 2, and then 7 divided 2 is not an integer. It's true. Okay. It's not integer. Right. Okay. Okay. Next. Okay. So there's some theorem here. Let's take 3 integers. Okay. Let's take 3 integers. And one of them is not 0. Then if A divide B and A divide C, then A will divide the sum of them. If A divides B, then A divides a multiple of B. And thirdly, if A divide B and B divides C, then A divides C. Okay. Okay, let's try and look at the first one. So if A divide B and A divide C, suppose A divide B and A divide C, want to show that A divides B plus C. Okay. So what does it mean by A divide B? We can write B as a multiples of A, right? So, okay. A divides C, so we can write C as a multiple of A. Right? But we want to show that A divides B plus C, which is B plus C is a what? Is a also a multiple of A. Okay. So this is what you want to show. So now you can take the sum, okay? B plus C, okay, which is AM plus AN. Okay. Then you can factorize it to get A plus N by A, where where M plus N is in the integer. Okay. So we found that B plus C is a multiple of A, hence A divided B plus C. Okay. So similarly, you can do it for part 2 and part 3. Okay. I'll try uh, two, two, two. Okay. So what's important with this is the next one. So let's copy this first and then we will prove the next one. Okay, from this corollary theorem here, we can prove this corollary. Let's take uh, A, B, C, and Z, okay, and A is not 0, such that A divides B and A divides C, then A divides the sum of multiple of B and C. Okay. M and N can be different. M and N. Or maybe we prove this one. So since this is a corollary, that means this theorem here follows from the previous theorem again. So this corollary follows from this theorem. But this theorem, it tells you that you can divide sum of B and C if you divide individually. But here you got multiple of them, right? So you need to think of a way to combine part 1 and part 2. Okay. So and maybe I give you 2 minutes let you think of how to use part 1 and part 2 of this corollary. So you can discuss with your friend. Once you got it, you can share with come here if you want and show. Anyone got any idea? Anyone got any idea? Hmm? Any idea? Okay, so you notice that actually this condition here is the same as the condition of the theorem. Okay, so now suppose we got A divide B and A divide C, right? Okay, we got A divide. Then you want to show that A divides MB plus MC, okay, for all MM. Okay, so since A divide B and C, we can use part 2. Okay, theorem part 2. Okay, so if A divides B, then A divides the multiple of B. So A divides MB for all M in Z. Right? And A divide NC for all N in Z. Okay. So maybe you notice that I sort this term here. Okay, it's because the multiplication of integer is commutative. Okay, so by part 2, we can divide the multiple of B and C. Then we can apply part 1 to get that A divide the sum of them. Then by theorem part 1, A divides MB plus NC for all MN in Z. Since let's make this since A divides MB and A divides MC. Okay. So if you want to add on here, so you can write since A divides B. Okay. So you satisfy this condition here, and this is a necessary condition, and then this is the sufficient. This is a sufficient condition. This is a necessary condition. Okay. Yeah. So if you have A divide B, A divide C, and then A will divide the multiple of the sum of multiple of B and C. Okay. Next. Okay, next we will do the division algorithm. So what's division algorithm? So let's take an integer. So let A be an integer. Yeah. Then there's a unique Q and there's a unique R with 0 greater than R and then less than D. Okay. So what's the relation between these Q, R, D, A? So the relation is such that A equals to DQ plus R. So maybe we do an example because it's easier to see. So for example, we have just now the example we got is 7 equals to 2 and 3 plus 1. Okay. So So here the A is this part here, and then D is this part, and then this is Q, this is R. Okay. So the claim here is every number you can do the division, and then you will always write in the unique form. Okay. And then the remainder here will be always less than the divisor. Because if this is more than 2, like 3, 4, 5, then you can just add another 2 in, right? So the remainder here is always less than the divisor. Okay, so in this case, we will call the A the dividend, Q the quotient, D is stand for divisor, and then R is the remainder. Okay, quotient is because, like, for example, 6 equals to 2 times 3, and it's 6 divided by 2. This is 2. So this thing is called quotient. Okay, so the 3 is the quotient. And then in this case, we have Q, we call it A div D. Okay, A divided by D, you get the quotient, right? So A divided by D. And then the next one is you need to take note about this because later we'll use a lot. So remainder is A mod D. Okay, so A mod D will get the remainder. This is the mod. Okay, so remember this, and then we will use a lot later. A mod D. Okay. Okay. Okay, yeah. So we will introduce modular arithmetic now using the division we learned just now. Okay. So definition. So if A and B are integers and n is positive integer, okay. We only mod with a positive integer again. So that's why we set it as a positive integer. Then we say that A is congruent to B and congruent to B modular M, and if M divide A minus B. Okay, and then we will write A runs to B more. So this part, this is modulus. Okay, and then the whole thing is called. So if A and B are not congruent, not M, then we write A not congruent. Okay, so that's mean if two things are congruent, we give example. For two things are congruent, for example, so just now we got 7, right? So maybe we put 9, 27, or 2 maybe. Okay. So why are these congruent? Because if you take the difference and take the difference, you divide by 2. Okay. So 2 divides 2. Right? Does that make sense? So if you want to say that two numbers are congruent, modulo M, So you take the difference of this number, then you divide by the n. Okay, so you must have three number. Start with three number first, three integers. Okay? And the n must be positive. Okay. So then, okay, there's a theorem. So this theorem will help you to do to check this congruence easier. Okay. So actually we can check the congruence using the remainder. Okay. So what's the statement? So similarly we take A, B in Z, okay, and then N in the positive integer. Okay. Then so how to check two numbers congruent? Okay. We can check it by the remainder. So if you check the remainder is the same, then they are congruent to each other. Modular. Yeah. Not sure maybe before running into the proof, we will see how to use this. So just now we say that 9 and 7 are congruent mod 2. Okay. We check the definition. So we take the difference and then divide by n. Okay. But now this theorem tells you there's another way. So this way is you check what is 9 mod 2. Okay. Which is what? 1. Yeah. So because 9 equals to 4 times 2 plus 1. Okay. So similarly, we got 7 mod 2 is 1. Okay. So if they are the same, they have the same remainder, then they are congruent to each other mod 2. Okay. So notice that you see here I put three line here, but here I only put 2 line, right? So these are different equivalent. So the equal here, this remainder here, because these are number, right? These are number. So this is equal as a number. But here I put 3 dot here because these two is not equal as number, right? But they are equal under the modulo n. Okay. And this is equal in this sense here, the congruent sense. Okay. So there's a difference, huh? Yeah. Huh? Which one? This one. 2 divide 2. What are you saying? Number 7 is 2, yeah.
What does the different expression mean?
Huh?
To divide.
Yeah, divide. What do you mean one? You mean the whole? Oh, okay. I mean, okay. I mean, okay. Okay. I'm being lazy, so this is this. Okay. Yeah. Okay. Yeah. Okay. Good. Let me see. 9:35. Let me see. Okay. I think we got time. So, do you see? Okay. Maybe we just see one part of it. So suppose one way. So suppose A suppose the remainder is the same. Okay. Suppose the remainder is the same. We want to check whether A congruence to B. Right. So remember how to check A congruence to B? You need to take the difference. You need to take the difference and then show that it is divisible by M. Okay. Yeah. And do you want to see why this makes sense in the just now the clock example just now? Right. Just now we say that just now what did we say? So just now we said that 3. Just now we say that from the motivation, right? We say that 13 is congruent to 1 mod. So because curve divide 13 minus 1. Okay. So actually we use division to define the modular arithmetic. So let's try come back. Okay, so this is our goal. So we need to able to compute the difference of A minus B. So we didn't prove the division algorithm, but we just use the fact that we can divide A by M, and so by division algorithm. I think it's proved in the textbook, so if you want to see algorithm, we can write A equals to M Q plus R for some unique M and um, unique R. Okay, for some unique M and R. But A, similarly, we can write B equals to, let us write M1, R1, M2 cube plus R2. Okay, we also can write this. But not that this R1 here, okay? So R1, what is R1? R1 is A mod M, right? The remainder, okay? And then A mod M is equal to B mod N by definition. Okay, maybe I write it this way. Mod M by assumption. Okay. And B mod M is actually R2, right? So actually R1 is equal to R2. Then we got A minus B equals to M1 Q plus R1 minus M2 Q plus M2, which is equal to M1 Q minus M2 Q, since R1 equals to R2. So you can cancel out the R1 and R2, which means, why did I use?
Should be Q1.
Yeah, right. Correct. Yeah. So it's not M is the difference, so Q is the difference. Yeah. Correct. Okay, so this become a M times 1. Okay, so M divides M minus B. Okay. Okay. So similarly, you can try do the other way. Do the other way. Okay. Oh, 9 minutes. Okay. Okay, next one. Okay, I think this theorem will come in handy in the later part of the topic. So similarly, we got positive. Okay, so if uh, let me see. So the statement is A and B are congruent to each other modulo M. Okay. If and only if there is a K Z such that A equals to B plus K. Okay. So this one is pretty straightforward to see, right? Because if you write out what is A congruent to B means, is actually you take the difference and then it is a multiple of M. Okay. So if you just move across, then you get this term here. So this is this direction. But if you start with this equality, then you can just move the B to the left hand side, which is A minus B plus Kn, which means that A minus B is a multiple of M, and then M will divide A minus B. Okay. Yeah. Try to good exercise to write the whole thing up. Right, so okay. Okay. Next. So next we can combine the congruence together. So if we got A congruence to B, okay, and C congruence to D, okay, we got two congruence together. What do you think we want to do? Put two things together. We want to combine them. We always want to combine them. Like in logic, in set, we always want to combine them. So how to combine them? So we can add them together first of all. So the result is we can add the left hand side, and we also can add the right hand side. Okay, and they are congruent to each other. Again, mod M. And we also can multiply on the left hand side and also multiply on the right hand side. And again, they are congruent to each other. Okay. Yeah, so you can try this exercise as well. If you do this exercise, it will like strengthen the understanding towards the definition. You just use definition. Just write out what it means to be congruence and then use the division. Okay, I use hint here. So use division algorithm to help. Okay. So write it as a in the division algorithm form, and then you can do the computation. Okay. Next. So next. So next. So next. So you can actually simplify with this theorem. Actually, you can simplify your calculation. So what do I mean by that? So let's say if you want to add two number together, and then you want to compute up to mod m. It's actually you can take the mod m on the individual term. Okay, you can first reduce the two term first, and then add them together, and then reduce again. Okay. Similarly for products, if you want to compute the product mod m, and notice that I use double line equality here because this is a remainder. This is number mod n. It's not congruent. Okay. And then you can also reduce individually, okay, and then multiply them. Then mod again. Okay. It may seems that here got more work, but imagine you got like out billion digit of numbers, okay, 2 billion digit numbers. You want to multiply them together, and then you take the mod. Okay. So the multiplication sometimes takes more work. So instead, you can just reduce one by one first, okay, reduce until mod m, and then make it smaller, the remainder, and then you mod again. Probably faster than you take the multiplication. Maybe addition is okay, still okay, but multiplication of billion of digit maybe is harder. 2 billion digit multiplied together. Okay? Yeah. So this one you also can try proof using proof using previous theorem. Using previous. Okay. So okay, I try to explain the structure of this modular arithmetic. See, you guys will get confused. Yesterday there is very damn confused. Okay, so in this modular arithmetic work, okay, we look at this set here, Zm. So we fix an m. For example, okay, let's have an example in mind. So maybe we fix Z5. Okay, actually Z12. You already see Z12 before. I use it as an example in the sector. So it's 0, 1 up to 11. Last time I used 12, so just change the 12 to 0. Okay, so in this world, you only have n integers. So I define a new addition. Okay, I can add them together. So it's a plus and a subscript m. Okay, plus and subscript m. A plus b. Okay, is equal to what? So this is what I define. I define a new addition and a new multiplication. Okay, subscript. So it's first you take the number and then you plus them together. Okay, you plus them together. And then maybe it will go out, right? So for example, in this case, you should imagine in your mind. So in this example here, maybe we got 11 plus 5, which is 16. But 16 is not in the set, right? So how? So we just mod m again, mod it back. So it will jump back into the set. Yeah. So if I take mod m, so in this case it's 12, I'll get 4. Okay, so it jump back into the set. So you remain inside the set. And multiply, similarly, you can multiply them together first and then you mod it back. Okay. So why we introduce this structure here? So actually this share a lot of shares properties, same properties, similar properties with the normal integer. Okay. So for example, the closure. Okay. Closure means so let's take A, B, C, Z, N. So if you do A plus B, okay, so the plus here is a special plus. We got what? is still in Zn, like what I described just now. If you multiply them, it's still in Zn, because everything are head mod and hit the remainder. Okay, so the remainder is always less than the divisor, which is m in this case. And then it is associative. Okay. So the process is associative. So for example, like am plus b, a plus b plus c is equal to a plus m. So do b plus c first. Okay, so this is associative. You also can do it on triple multiplication, right? So you can do AB first, and then it's the same as you do BC first. Okay, and then commutativity. Okay, I always talk about this commutativity. So you can sort two of them. So A plus B is equal to B plus A. Okay, under this new addition law, and also under the new multiplication law. Okay. It's not too far away from the addition and multiplication in the integer, but after we do the operation, we take mod and okay. And then we also got identity elements. Okay. Identity elements, for example, so what are the identity elements? So it's the 0 and 1. So you take A plus 0, you always get back A. If you take A multiplied by 1, you always get back A. So this one, there's a special name for it. This is the additive. And then this one is the multiplicative. Okay. And then what is 1, 2, 3, 4? And then 5 we got additive inverse. So additive inverse means, so okay, what is this? What does this mean? So this means, okay, let's call it M. So this means for every A, okay, for every A, there's this an M. Okay, I don't want to use M already. Because this is mod M, so maybe change another set M such that A plus MP equals 0. Yeah. Yeah, so why is this true? Maybe let you think why is this true. So what P can you take? And then we will go into break, and then we'll come back again. Come back 10:05. Okay. Let you think, and then we'll resume then.
I need to go to the clinic.
Clinic? Okay. Okay. Now.
I will be back on the maybe later.
Okay. The quiz will be 10, 11.
Yeah,
Okay.
如果是错的话，我们给这样子的弄的
OK，如果是对的话，OK。什么？
像这个理解题的，因为它的 very 就是比较单纯，它就是讲理解题是等于这个的。这个是我在课本里面看不到的，
看不到啊，
课本里面看到，然后讲义里面没有。
对，
我直接讲白这个东西，因为我想不到它的名字。
我觉得可以。其实
free 的那个
不是，其实这个其实已经算是 definition 了。怎么说呢？因为这个的意思是说在 在 B 里面不在 A 里面，对，在 B 里面不在 A 里面，是说在 B 里面在 A 外边哦，也就是这个，其实就是 definition。虽然是有一点不是太直接，但是
但是我是在课本里面看到还有一个就是这个等于这个equivalent，来用，因为理解我想不到很好的解释方法。
没有这个其实是 definition of B 减 M， 就是其实是 definition of B
就是它的
因为我也是直接用在我的那个 tutorial 里面，应该是
然后老师这个 definition of 这个可以直接反了，
就是
它是1的直接变 n。
没有，你应该没有这一行了，因为如果你要放这个弯弯的话，不是，这弯弯的两边一定是 set 来的，不可能是 proposition。
两边一定是 set
proposition。弯弯的话，两边一定是 proposition。你就 intersect 两个 set 吧，你不可能 intersect 两个 proposition。
就是
这样的东西。
就是我如果换成 proposition，如果是这样子写的话，我的决定要是这样。
因为这个是这个的 definition。
所以首先做这个就像这样。
对，你看你这边又乱了，你看你这个，你看你乱，这个是 n 哦，这个 n 只可以跟 proposition 一起，你不可以 n 两个 set 在一起，没有这样的东西。
像第一个是应该是1的，然后
对，第二个还是1的。
这个是1的，然后减的，
这个也是1的，
这个也是1的。
尖的话一定是变成这个，因为你尖的旁边不可以放两个 set。
尖的旁边
尖的旁边一定是 proposition， 弯的是 for set。
就是一开始我这样子是1的，然后如果我 set 成左边一个右边一个就要变成尖，
因为这两个是 proposition 的，然后这是它的 definition。什么是 composition？
打开那个是什么？
没有，这就是 definition of 这个东西。
这个对
definition of 这个才能够打开。
这样没有了，这样没有，直接就 simplification， 然后 A。
可以。可以。
像我在误会有什么？
这个怎么讲？
denomination，
然后你要 prove 什么？
但是要 prove 这个等于 no set。
是啊。
这个是那题这6的。
感觉你这个步骤跟我不一样是吧？
完全不一样。
OK， 我觉得可以问，应该可以问。
因为这个是我那时候自己做的，
应该可以问
的，
应该可以
问，就很什么，也不是就不是很正经这样啊，
很正经。
因为那时候老师你还没有讲过这个 tutorial 模式。
哦，你这边没有，你这边好像你你这边应该有一个挂弧哎，你这边有一个挂弧的，哦，但是不用紧，因为它是没有钱的，因为它是 NS，因为它 associative，
然后后面 dative，然后我就兑换，然后这个跟这个 complement，比较
可以，我觉得可以，
我那时候你 proof 在哪里？
我觉得可以，可以，它是等于还是 subset 啊？
哪一个？
你这个只有 subset 罢了，
我看一下题目。
你就挑这边去这边
他这个是讲 to show that，
啊，
他题目是讲 to show that，
我知道你这个只有一边吧？它打
要 show 回去啊。
没有，它题目是怎样？它是 subset 一边还是等于？应该是等于啊，如果我看。
是，如果因为要 proof 回去另外一边的话，我就瞎了啊。这样子
没有，另外一边比较简单
啊？
它 set 不是empty set 不是 subset of every set。
empty set 是 subset of every set。
啊，
哦哦，
问题啊，
我 get 到了，get 到了，是不是？没有，就 get 到了，想起来了。empty set is
咱们这个
呀，
可以具体一点吗？就为什么这个是 on 多的时候，这个 f 一定是 on 多 f 我觉
这个上次上游啊，你要听到。
因为你要讲具体吧，因为这是具体，
不是你再讲多一次吧，我看能不能 get 到。
你要例子是这样。
不用。
OK，来，所以你看啊，所以你假设它的 composite 是 on two，你要说的外面这个东西是 on two 嘛？
对。
外面那个东西是 on two，就是说给我一个东西，这里我可以找一个 B map 去 C，对吧？是吧？如果 F 是 on two 的话，我可以给我一个 C，我找一个 B map 过去。OK，那我就先给我一个 C 里面的东西哦。OK，我试下能不能找 B 里面的东西的，这是我的目标。OK，但是我知道 F compose G 是 on two，意思说 F compose G 是从哪里下来？
就 A
H C
H C
C
H B B 加 H C 是 H C，所以是我现在有一个 C 的东西哦。F G 是 on two，代表我可以在 A 里面找一个东西，such that F G map 那个东西去这个 Y， 可以吗？然后我叫它叫它 X 哦。对不对 ？OK，但是我现在 X 里面有这个东西啊，我可以用 G 把它 map 过去吗？一步一步做嘛 ，compose 嘛，对吧？
然后 on two 的话是最后你可以找到一个 match 的，然后你最后要 match，你代表前一个也是 match 的啦，就是有连到，是这样。
没有 on two 的意思就是说每一个
image 都有
它的
去
image，
每一个 image 肯定有一个 pre-image，但是是每一个 code domain 的 element 都有一个 pre-image。当那个 range of 那个 f 等于那个 code domain，可以明白吗 ？range 等于可以啊，可以明白，可以明白，可以明白。说 range 或者 image 我们是写成这样的 ，OK，这个东西，这里面的东西肯定是有一个 pre-image 的，所以这里面的东西是什么？OK，你不要吓到，忽然间我写这样长的东西。这个东西其实要讲的东西是这里面的东西，OK，是有一个一定有一个 pre-image under 这个 F 可以到达它，你可以看，就是说 C 在这里，B 在这里，OK，这里有个 T，这里有个 F，然后它可以送过去。 OK， 这个是它的 emax 跟这个 range， 但是如果 onto 的话，就是代表每一个里面 C 的东西都可以写成这样子的东西，就是每一个 C 里面的东西我都可以找一个 prime， 这是你要做的，你要找有没有 B 可以透过 F map 回去 ，OK， 例子啊
就是 F of G，
这样，
然后我的 F 是 onto，然后它里面的东西代表它的 G 是，我 map G 的话也是 map 得到，然后我才 map 到 F。
说现在你有这样说，你也有一个东西是这个是从 A 到 C， 对不对？对。说你要说这个东西是 onto， 所以意思说每一个在 C 里面的东西，你要找一个 B 里面的东西 ，such that f(x) 等于 y， 对不对？对哈。但是对，你要 prove 这个，但是你告诉你的是这个东西是 onto， 对不对？
对。
这样意思说每一个 C 里面的东西有一个东西可能叫另外一个名叫 Z，OK 好叫 Z 在 A 里面 such that F compose G on 这个 Z 的话是 Y， 对吗？合理吗？我只换方程吧，同样的句子我只换方程吧。这个是 F 是 onto， 这个是 F compose G 是 on， 可以理解吗？
所以我们 prove 到这里就可以了。
没有 proof， 还没有 proof， 我只是把全部要的东西写出来吧。这个是要的东西，这个是need to show， 这个是要求的东西，然后这个是given的东西，这是你有的东西，这是你要的东西。对，你要找这个 x， 但是你有这些东西。
然后我们要讲 proof。
OK， 然后讲 proof， 然后你看这个东西 composite 的 definition 是什么 ？F apply on G set 等于 y， 对不对？你不觉得这个东西长得很像这个？
对，我也是这样理解。可是然后下面讲写，
然后下面要讲写，下面你要 argue 就是说你怎样找到这个 x， 谁是你的 x 现在？
这个我的 x 是 GX
所以你就说 take x OK， then f g z 就是 y， 那你就找到这个呀，因为这个东西是在 B 吗？你找到一个在 B 的东西 ，such that 你 apply f， 你拿到 y。OK，
这样说我们考试的时候要这样子写，还是这样子写就可以了？
两个是一样的。
这个有点抽象啊，讲真的。
这个可能比较简化。
对。
简化，如果你可以这样一样的，
就像我讲
可以这样写。
可以一样。一样。这个是前面的是 onto 的话是前面的是 onto， 然后 one to one 的话是后面的是 one to one。
对。
但这 one to one 的是为什么？为什么是前面的是 onto， 后面是 one to one？ 因为它有一个对。
那是 C。你说有没有一个原因？
对。规律啊，好像
规律。
因为一开始我想的是 FOG 它是 onto 的话，然后我把 G 后面的 GX 想象成 F 的那个 X， 它就肯定也是 onto。可是这个 one to one 的话，它是后面的是 one to one， 不太理解为什么。
不太理解
回去。
你反着理解可能比较容易。Control positive。
反正
如果里面的那个不是 one to one 呢，意思说已经有不同的东西被送去同一个东西。这样的话，你再 compose 还是不同东西会送去同一个东西
它也不会是 one to one
啊，它也不会是问题
哦
啊。你用 contrapositive 可能比较例子比较
可以，明白。
就一个答案它可以有很多个 input 这样的，很多个 x 放进去。
啊。他是问讲你写中国是里面，
对，
这个是那个题目。
应该
OK，
大家要 x show that
好，嗯，
所以这个也是 two way 的 proof 啊。
呀，two way，
这样子就，哦，这样我 proof 了这个，我还要再 proof 回去。
哪个？第一
全部吗？这些 A B C D E。
因为这个只有 one way，就这两个有 two way，
等于就是 two way 啦。
对。
哦，MB set all set subset of all set，对 subset。
啊，对。
然后像这种的话，
那你就要说这个东西在这个里面，但是我觉得好像我不能够直接这样去，所以我是用 contrapositive。嗯，
就是如果是换成这样，就是它有那个 addition 啊，我再放这个东西进去。就比较好概念咯，可能我要看那个表做，让它配出来。
可以试一下，你可以试一下。
哦，就是
你可以试一下。
等于就是出位。
对。
subset。
应该我讲几点几点开始来着？我们零 OK 过了。OK，hello testing。Okay, let's come back here. So, okay. Anyone got any idea on P? So what's the number that add to A you get 0? Okay. Since I said that exists, you must be able to write it down. Okay. So we can take P equals to n minus A. Okay. N minus A works because A is always less than this again. So because since A is always less than n, so because the remainder is always less than the divisor, so if you take n minus A, you will get something in Zm. So maybe you will ask, why not just take A plus minus A is also 0, right? Right. A minus A is 0, right? But right, I mean, why not take minus A? Okay. So the concern is in our Zm, there's no negative. So this number here is not in Zm. Okay. So using n minus A, you will make sure that this number is in Zm. And then 6 is a distributivity law. Okay. Distributivity is remember the n and all thing. So here we got A dot m times B plus C is equal to A dot m B plus A dot m C. Okay, so it's the distribute. Okay, so these are the structure of Zm. Yeah, I think during the rest, some of you asked some very important questions, but I want to try to change the mode how you ask questions. So, what if let's say every break, maybe 5 minutes before the class start, and then all of you will pass a question to me, maybe in paper or you email me. Then I start answering during the start of the class. You think this work or not? Instead of you, maybe you say you don't know how to ask on the spot, or you will start when you're asking. Does this work? Like before 5 minutes, you can start emailing me or you pass me a paper, and then when the class start, and then I start answering the question. Instead of you ask on the spot, maybe you shy or maybe you will get stuck. What do you think? Huh? Can't remember. Yeah, can't remember what to ask. So you just for the whole week you try to write down all the problems, and then 5 minutes before the class start, you send me the problem, and then we answer during the start of the class. What do you think? What do you think? Yeah. Okay. Okay. I offer 2 ways. So you can email me 5 minutes during the break, and then I answer during the class, or you can straight away ask in the class. So both work. Okay. Yeah. So you can email me and then pass me a paper, and then I can try answer, because if I answer to you only, other people also got similar problems. Then if I answer in front of the class, then everyone will learn. Okay. Okay. Next part. So next part, we'll go into primes number. So and greatest common divisor. Greatest common divisor will be used in the crypto as well, or solving the congruence later. And primes is to use for breaking the numbers down. Okay. So let's start with what's the prime number. So prime number is also an integer. Okay. We still live in an integer world, which is greater than 1. Okay. It's called prime if the only positive factor of P are 1 and P. If not, P is all composite. Okay, let's take an example. So when I talk about this definition, right, if you don't understand, you just follow my flow, follow my definition, and then in my definition, I will refer back to the, follow my example, and then my example will refer back to the definition again. So for example, 7 is a prime. Okay, 7 is a prime. Why? Because 1 divide 7 and 7 divide 7. Okay, and normal. And okay, only, right? Because 2 doesn't divide 7, 3, 4, 5, 6 doesn't divide 7. Only 1 and 7. So these are the only 2 positive factors. Okay. 1 we doesn't 1, although 1 divide itself, 1 divide, okay, 2 times 1 divide itself, and then it divide itself. So we don't call it a prime, so we leave out it. So greater than 1. Leave it out. What is composite? For example, 6 is composite. 6 is composite. Okay. Because 1 divide 6. Okay. 6 divide 6, of course. You also get what also what factors you have? 2 divide 6, and okay, 3 divide 6. Okay. So it's composite. Okay. Then use this to understand this definition. Okay. Okay, next. Next. So how is this useful? So like what I said just now, the fundamental theorem of arithmetic. So every integers can be greater than 1, okay? Can be written as a product of primes. And written uniquely. And it's unique. Only one way to write. Up to order. Okay. So every number you can break into primes. Okay. Up to order. This is proved by I think the textbook using another induction method. So you can refer if you are interested. So okay, maybe let's see. So for example, how to break 8. So you can break 8 into 2 times 2 times 2. Right? What number you want to break? Maybe you want to break 51 is 3 times 17. Okay, there's only one way, and then up to order. So how to check? Okay, so if n is this theorem here. So how to check something is a prime? This theorem will become in handy. So if n is an composite integer, then n has a prime divisor less than or equal to square root n. Okay. You can refer to a textbook if you want for the proof. So, but how to use this theorem is very important here. So maybe you want to show that 137 is a prime. So you consider the contrapositive. So if n doesn't have a prime divisor that is less than or equal to square root n, then n is a prime. Not q implies not p. So that means I just need to check what is square root 137. Okay, maybe you can estimate with 144, which is 12. So what's the prime that is less than 12? Like 11, 7. I should start 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. Okay, there's only 5 of them are prime. So you just check. There's only 5 of them. You just check whether they divide 137. Okay. So since 137 are not divisible by 2, 3, 5, 7, 11. Okay. So I use the mod language just now. It's not congruent to 0 mod this prime number. It follows that 137 is a prime. Okay. So you don't need to check all the prime divisor for 137. You just need to check those those prime that are less than square root 137. Okay, so you reduce your work. Because initially, if you want to check whether something is a prime or not, you need to take you need to check whether all the number before it is divisor of 137, right? But with this theorem, you just need to check this those prime that are less than the square root of 137. Okay. Okay. Next. Next. Okay, this is the basic stone of cryptography. So this theorem is I think it's called Euclid's lemma. So there are infinitely many primes. Okay. So that means you can find infinitely many primes in the integers. So maybe we just quickly prove this by contradiction. And this is a classic proof. Maybe you should see it once. So proof by contradiction. Assume there are only finitely many of them, right? Assume the negation of this statement. Assume finitely there are finitely many primes. So like P1, P2 up to Pn, say. Yeah. Then we can consider one number here. We consider Q equals to P1 product of Pi up to Pn plus 1. Okay. If Q is a prime, okay, then we reach a contradiction. Why? Because at first we only said that there are only n of the prime numbers, but now we construct Pn plus 1, right? So this is a contradiction. So we suppose since if then we reach a contradiction. So suppose Q is not a prime. Okay. If Q is a prime, then we reach a contradiction. So we must go another path. So suppose Q is not a prime. Okay. If Q is not a prime, that means there exists some Pi Pi in the up to there's some previous prime number that divide Q. Right. Okay. So remember we did the theorem just now in the start of the class. Then we have Pi divides Q, and Pi of course divide the product of primes, right? Because it's one of the I inside. So Pi divide the sum of the multiple of these two numbers. So in particular, Pi divides Q minus P1, P2 up to Pn. Okay, which means Pi divides 1. Since Q equals to P1. Okay, but what number divide 1? 1. But 1 is not a contradiction again. So hence we reach another. Okay. So the original assumption is wrong. Okay. So this proof is not constructive. So I'm not constructing new prime number for you, but I just tell you that there must be more primes. One more time. One more time. Okay, okay. Okay. So we want to prove that there are infinitely many primes, right? Okay. We first assume that there are only finitely many. So assume the negation. Only finitely many. And then we try construct another number here, which is the product of the finitely many primes plus 1. Does this make sense or not? Yeah, product. This is the trick we use so that we can reach contradiction. Yeah. Yeah, why is plus 1? Like plus 2, if plus 2, then this maybe doesn't work already. Because if you want to divide 2, so got 1 and 2. So maybe the PI is 2. If you put 1 here, then we try to divide the sum of this combination, then you will reach that your prime have to divide 1. But what number divide 1 is only 1. And 1 is not a prime. But you say that you start from a prime. Yeah. Okay. Huh? Not really.
Not really.
So okay, so the idea is like okay, I mean the idea is so this is uh so contradiction is like assume not P and then prove that not P is wrong and then P is true. So assume not P and then prove that not P is false and then P is true. Okay, so assume not P, yeah, and then you keep going and prove that not P is false and then P is true. Okay, I think this step here. So if you construct a new, this is a new number, right? So this is different from all P1 up to Pn. This is a new number. If this is a prime, why we got a contradiction? Because first you only assume only the n of them, but you construct another extra one. So this is contradicting the finiteness of the prime. Okay. Okay, maybe I write down what's the contradiction here. So this is contradicting the assumption that primes are finite. Okay, but this one contradicts what? Contradicts that is no. Okay, two different contradictions. Okay. Okay. Think about it. Okay. If got question, then we cover again. Yeah. Yeah, two different contradictions here. Okay. So then they ask another question. So they got observation of twin primes. Okay. What is a twin primes? So for example, there are primes that are 2 apart, like 3 and 5, 5 and 7, 11 and 13, 17 and 19, okay, 29 and 31, 59 and 61, okay, 71 and 73. Maybe you can keep going, keep going, keep going. You can find, but you're not sure whether there's an end or not. Okay. So the question is, are they infinitely many twin primes? What do you think? Do you think yes or no? Huh? Yes. Yes. Why? Can you prove? Yeah, don't so actually this question is open. Okay. Yeah, if you know how to prove, then maybe we'll change the way of crypto. Oh, this question is open. Thanks. Okay, next we introduce the GCD, common greatest common divisor. Let me try another way. So for example, the common greatest common divisor is of 8 and 64 is 8. Okay. Like the GCD of 2 and 6 is 2. Maybe we pick another non-trivial one. For example, 1, 8 and 10. Okay, this one is 2. Okay. So what's GCD? So let A and B Z, okay, such that A and B are not both 0, such that both not 0. Okay. So what's GCD? The largest integer D, such that D will divide A and D will divide B. It's called the greatest common divisor. A and B. Okay, denoted by G, C, D, or B. Okay, so you want to find a number that divides both A and B, and then it's the largest one. Okay, GCD. So if the GCD is equal to 1, okay, we call them relatively prime. They might not be prime number, but they are relatively prime. So for example, GCD of 8 and 9. 9. Right? So this is 1. Okay. They are not prime, right? They are not prime. 8 is not prime because 2 divide 8. 8 divide 8, 1 divide 8. 9, 3 divide 9, 9 divide 9 is 1 divide 9. So they are not prime, but they are relatively prime. Okay. And then next one, so if you got a bunch of integers, so n of them maybe, they are pairwise relatively prime. This one will be a condition used next week. So I need to introduce this word first. So they are pairwise relatively prime if AI and AJ equals to 1 for the AJ between n and 1. Okay. So you need to check any two of them. Its GCD is 1. Okay. I got 40, got 10 minutes. I got 10 minutes. So can you go back and read LCM? LCM, okay, so let me write out. Please. Because LCM, we won't do much computation with LCM, but it kinds of link with GCD. So I think it's worth to read. Because some part, I don't say you need to read. I don't say that you need to read because it's whether you can read on your own time. But this part here is related to GCD, so maybe you can read. Please go back. Let's see. LCM. So it's the low list. And I want to spend more time with the algorithm because it's very important for your test. Oh, that one more important. This one you can read because this one got nice consequence between GCD and least common multiple. Okay, let's do the real business here. So Euclidean algorithm. This is the main takeaway today. Okay, so what's a Euclidean algorithm? So we know that given two number A and M, B and Q, we can do the division algorithm, right? B and A and B, we can do the division algorithm. Okay. And this is by the division algorithm. Then we can find the GCD of AB. Okay, we want to find this will provide a way to find GCD of AB instead of you just testing the factor, and then find the largest one, right? So this way is a systematic way to find the GCD of A and B. So you can divide the bigger one by the smaller one, and then you can look at the next GCD, which is the B with the remainder. Yeah. So for example, let's do example first and then do example first. So how are we going to use this? So for example, we want to find the GCD of 51 and 9. Okay. So by this lemma, right, you need to use the division algorithm to write A into this form. So my A is 51. My B is 9. Okay, what's Q? What Q here? Okay. 5. 5 plus 6. Okay. Okay. And then next you use 9 and 6. Okay, you do the division algorithm again, which is 9 is equal to 6 times 1 plus 3. And then 6 is equal to 3 times 2. Okay. So by this by lemma, by Euclidean algorithm, by Euclidean algorithm, GCD of 51 and 9 is equal to GCD of 9 and 3, okay, which is equal to GCD of doing something wrong. 9, 59. I think I go too fast. 9 and 6, and then 6 and 3, which is what? GCD of 3 and 0, which is 3. Okay. Yeah. So instead of you, go and try test all the factors and then find the largest one, you can do the division algorithm and then you can find the GCD using the last one. Okay. Okay, this is Euclidean algorithm. You will get a lot of chance practicing using the practice I take. So you ignore the instruction in the book and then just use my method and then go and find the GCD. And then the next one is called the extended Euclidean algorithm. By the way, if you are interested in the proof, you can go and look for the textbook. And then if you want to discuss about a proof, I'm okay inside the lecture or outside during the office hour. So let's say, okay, we got this in we got this GCD here. Let me write down what's the condition here. We got a GCD. Actually, we can express the GCD back to the sum of multiple of A and B. Okay. So the theorem is the GCD. Just now, for example, just now we found that the GCD, this is example. For example, GCD of just now 51 and 9 is 3, right? So we can write 3 as S sum X times 51 plus sum B plus time T. Okay. So how to find this S and T? How to find is what this extended Euclidean algorithm do. So let's copy this that here. This. Okay. So what you do is you do the backward Euclidean algorithm. Okay. So from here you can see that 3 you can write it as 9 minus 6. Okay. And then here 6 is equal to 51 minus 5 times 9. Okay. So let's try. So do the backward Euclidean algorithm. Okay, let me block this out. So 3 is equal to 1.6 minus 9 minus 1.6. And then 6 is equal to, okay, let me, if you are really, you get 51 minus 9.5, yeah, which is 9 times 51 plus 5 times 9, which is minus 51 plus 6. Okay, so now you write it in terms of B, B, A, and B. Okay, so this is, you can understand it as a backward substituting of Euclidean algorithm. So one is a standard algorithm. One is Euclidean algorithm. You do the division algorithm all the way down, and then find the GCD. And then a standard Euclidean algorithm is you go all the way back, and then you can find that the GCD is a linear combination of these two numbers here. Okay. So these two you get practice in the tutorial question. But any question on this two algorithm? There's no proof here. This is just telling you how to do. Any question? Is it clear? Oh, confused. Okay. 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 Okay, next, before we go into the break. Okay, so before going to a break, we got a lemma here. So let's take A, B, C positive. Okay. A, B, C positive. And then the GCD of A and B is equal to 1. And A divide BC Okay. Then A will divide C. Okay. So if you have A divide BC, a product, and then you know that there's no common divisor between A, B other than 1. Then you can deduce that A will divide C. Okay. And you can see the proof. And then what's important here is the next theorem. Okay, this will help in computing the modular arithmetic. So let M be a positive number and A, B, C in integer. So if AC congruent to BC mod M and GCD of CM is 1, then A is congruent to MB mod M. So that means if they are congruent to each other, the two products are congruent to each other, containing C as a factor, and C and M has no common divisor other than 1, then you can just cancel it. Yeah. You just cancel it and then you will find that A is congruent to mod M. And then it's a good exercise to prove this. Okay. Okay. Yeah. Any question on that? So take a break until 11:03 and then come back, we'll have a quiz. Yeah. Su Yang. 那你可以先去理解一下这个。对，这个就是 union 的 A1、A2、A3到 N 的。
所以我们就不可以这样取就可以。
是取那个最大 N 那一个半，我的不是拿全部诶。
全部是什么意思？全部你是说前面那些？
我那个 not 出来。
因为那个时候我们如果是讲的是 N 的话，我们直接拿 N，就是1到 N。对。
这个 N 是代表全部。
对，所以为什么它代表全部？啊
1加2加3加4加到 N。
哦，我知道了，你们好像看太快了，难怪你们好像不明白。
这个是 range 的话就有可能这样。
哦，你跳一条线，要线。因为 A1是，哦，我知道，看一下因为这个是 A1、A2、AN 嘛，对不对？对不对 ？OK， 这个明白了。然后 A1是什么？是这个东西写到了 I， 对不对？还写到1，所以这边是0啊，0、1啊。OK， 下一个呢？下一个长怎样？减2减1，0、1、2，可以明白吗？然后就一直到 N。
那为什么？
为什么？
N 2我的不是全部。
对啊，
就是从0写到 N。
那比如我再问一个更简单的问题了，这一个跟这个是什么东西？你知道这个东西可以写成OK， 这个
这个不是这个不是只是叫
那个下面的 A 第二个版，因为我
没有错，
它是一个 range 来的，它一直在扩大它的 range。
老师这个事情，可以懂吗 ？OK，
上面的
上面
很复杂，
对，上面
这个哪一个？选一个，
感觉全部都不会。
都很乱，老师。
你随便讲一个，你随便讲一个。
OK。OK， 讲第一个，对，第一个是什么东西 ？Union of AI。对呀，对，丢到完。所以如果1的话长怎样 ？OK， 你不懂这种题目，不是你一定要把1、2、3这样子写出来，一个一个写出来，这样你知道它长怎样。比如说1的话，它长成1加1 2，1加2 3，这样过。那2长怎样呢？2稍微2加1什么3，2加2 4，来过哦。然后你就看到 pattern 了咯。3的话就是3、4、5这样哦。对，那你看的话，你就看到，哎，它好像是越来越小，越来越小，对不对？对不对？所以如果你拿 union， 对，你要把它写出来，你才可以
知道，每一个你都要写出来，因为如果你这样，你可能看不懂那个，你是一个一个写出来，那你
就还有个 A 最大，B 最小的
啊，
也因为这样infinity嘛，它可以define最后一个，最后一个就是可能就是完全没有数字哦，你 define 不到。
你不会到最后一个，你到不了它，
所以它就完全没有。
对，最大 union 最大
啊，对，其实如果要证明这个是比较难一点，但是你要有一个概念了，有一个概念就可以了。这个哈，因为如果你假设这个不是 empty set 啊，假设不是 empty set， 反证法contradiction 哦，假设它不是 empty set 的话，它有个数字在里面，比如说你取了数字，你取一个数字，你写这个，不是啊，这样小，OK， 100也可以，100也可以 ，OK。那100的话，我还可以去到 A101啊，A101没有100哦，这样子它就不在那个 intersection 里面了。
一这种
infinity，OK， 但是 infinity 重点是 infinity 不是一个数字，infinity 不是一个数字，所以你 infinity 可以，因为 infinity 不是一个数字，所以没有 infinity 加1 infinity 加2，
我们就上个 M C 嘛。
对，没有错。
因为很好看嘛，第一个有 E，第二个就没有了。还有这往后，最后的那个 range 也有写。
应该是第二题哈，第二题，你的 set 是长成01、02、03、04，就两个嘛 ，OK。像你union的话，你是不是有01、02？哪一次出？就0、1、2、3、4、5、6、7、8、9、10。
大于0的。
Yeah，OK。你的 section OK 啊？0啊，因为全部在2就超出。第3是一个 interval 来的，所以它是01、02、03。interval 是说中间这些号码都在，比如说0.01、0.02、0.5、0.9、9.75，全部在里面，然后就越来越大，到5000，对吗？
1啊，为什么最小？因为我后面的 range 在慢慢变大，这样它的共生的就是在最小。
哦，不要放啊，它有减啊，它有负号，R 是
对不起，最小。
大过0可以，这个可以，但是我们会 prefer 用，如果能的话用回相同的 notation 哦，呀，如果能的话用回之前有的，呀。
也可以独立，可以让发号那种做做法。
周，然后
也是可以。
1、2、3、4、5、6、7、8、9、10，这样，你想这样，这样，对，你想这样，不可以，因为你写那个是 set 来的，这是 set notation，这个的 definition， 这个的 definition 是这样的，这个是一个 set 在 R such that x 小于 infinity 大于0，这个是它的表达方法，所以你不要把这个跟这个混乱。
太跳了，
Hello. Please return to your seat. Return to your seat. Return to your seat. And then I will pass the Yes, divide into 4 rows, right? And then the first person, can you count how many person in your row? And then collect the quiz paper from me. First person in the row, can you please how many? Count how many students in the row and collect paper from them. First person, please help me count the student in the row. 15. Okay, 等一下 wait. 15. And then count the student in the row. 16. Count the student in the row. 16. No, I mean the whole row. 16. And then this one, 11. And then just for every, yeah. Huh? Oh, whole the everything, the last row. Just count all these. 15, huh? Okay. Okay, come and count and then get distribute. Yeah. Come and get. No, just your last row. 15, yeah. Okay. Come and get 15. Come and collect the quiz paper and then distribute. 15. Once you get the quiz paper, don't start first. Just read. Don't start. 16. No. Count first. Don't start first. Close all your electronic devices and then face down your iPad or phone. Don't start first. Don't start first. You can write your name, uni ID, English name. Don't start first. Put down your phone, turn off your device, and then face down. Okay. Okay, now it's 11:10. There's one correction here. The task 2.2. I write it here already. So find a domain interval such that f is bijective on the corresponding range. Okay, 1:10. We got 15 minutes. We will end 11:25. Okay, start. Ask now.
you done done one. And I give you 1 more minute to clear check your name and then ID. If you are done, you can pass to the front. Okay, pass your quiz to the front. And then the first person help me to calculate whether it's the right number or not.
Eleven.
Hey, this one
这一组的，这一组，一起的。对，我们就交上来了，结果后面还有传来。
没有端呢哈。对，OK， thank you。
还有一个。
OK。Hello. Hey, how about the last row? Who? Hello, last row. Hey, who haven't submit? Hello.
Start with the tutorial question. Chun Wai. I thought you say you want to draw graph to show one-to-one. Why not? But what you wrote here is no score. Okay, my way of giving score is like, if you can't prove from definition, if you at least can show me that you know the concept, then you will get partial mark. Yeah, if you can't write the full answer, but you can write something that you can explain the concept, then I will give partial mark. Yeah.
Hello. Okay. Before we left, let's discuss a bit on this question, on this question. So 4.1.2, prove that 1 divides A divides 0. So you need to write A as a multiple of 1 and 0 as a multiple of A. Next, if A divides the product, A is not 0, then A divides B or A divides A. So it's false. So although 4 divides 4, although 4 divides 4, but 4 doesn't divide 2, and yeah, 4 doesn't divide 2. Okay. 4.1.10 is what? Since A and B are integers, non-zero integers, and then A divided B, and then A plus B are what? In case of. You can use contradiction in this case, because if you use direct proof, you don't know how to proceed with even and odd. That, yeah, thank you. Okay, this one proved by contradiction. So assume that A is even, and then prove that A plus B is even, and contradict. This one, 4.1.16 is the block number calculation. Mod 24, 1 day. Okay. 4.1.18. Yeah, this one is using the theorem that we have shown in class, how to do the modular arithmetic. Okay. And then decide whether a number is a prime. 4.3.2. 4.3.4, write the integer as a product of prime. So since 101 is a prime, so it's just 101 times itself, right? Prime. The only things that divide prime is itself and 1. This is what it means by prime. Okay. So this one is what? Find the find the integer that is relatively prime to 12. Okay. Where A is less than 12. In other words, there's no common divisor between A and the 12. Okay, 4.3.32. Yeah, this one you need to master this technique, Euclidean algorithm. Part B still short. Yeah, C. And then I use this as an example to explain the algorithm again. So you have to find GCD of AB. Okay. So you take the largest one, divide by the smaller one. Okay. Use the division algorithm, find the remainder. And then you take the divisor and the remainder, do the division algorithm again. And then take the divisor and the remainder, do the division algorithm again. And then until you found the GCD. Okay. Do the division algorithm with the divisor and remainder, and then keep going until you get the GCD. Until you get a plus 0, then you can stop. Okay. Then keep going. Use the divisor and the remainder, do the division algorithm, divisor, remainder, division algorithm, divisor, remainder, division algorithm, and then divisor remainder to the division algorithm until you get the plus 0. Then you stop. You will get the GCD here. Okay, so this is the GCD. Okay, and then 4.3.40 is the extended Euclidean algorithm. So you need to perform the Euclidean algorithm first, and then you found the GCD, and then you do the backward substitution. Okay, 1 equals to 9 plus 9 minus 4 times 2, and then express the remainder as 9 and 11 again, and then until you reach all the way back to A. Okay, right. 1 as a linear function of 9. B and C, so you do. So first you go and find the GCD first using the Euclidean algorithm and the lemma using Euclidean algorithm, and then you do the backward substitution. So one is 3 minus 2, okay, and then substitute the remainder again, okay, and then substitute the remainder again, and then substitute the remainder again. Okay, then you get all the way back to A and B. Okay, just keep practicing. I think this textbook question is like a bit long, very long. Always the GCD is just 1. But the GCD 1 meaning the two numbers are relatively prime. Yeah. So you can keep going. Do the division algorithm and substitute back the remainder. To substitute and yeah. Then all the way you will come back to the A and B. Okay. And E same, F same, G same, H same, I same. Oh, I include this 1.4.3.50. So this this statement says that if A is congruent to B mod M, then the GCD of A and M is the same as the GCD of B and M. Okay, I include this example is because this show you how to show that two GCD are the same. Okay, to show that two GCD are the same, you need to show that the set of common divisor is the same on both sides. Okay, so anything divides A and M also divide B and M. Anything divide B and M also divide A and M. This is how we prove. This is the technique used to prove the Euclidean algorithm. So that's why I include this in so that you can understand the proof and then try to imitate the proof for different segments. Yeah, so the set, if the set of common divisor of A and B are the same with the set of common divisor of B and A, then if you pick the largest guy, they also have to be the same because both of them have the same set. So how you pick the largest one is the same. So that okay. If there's no question, then we can dismiss. Huh? Oh, thank you. Thank you.